present my work, the PP10, especially the Chung-Yuan Christian University, because Niigata University is Chung-Yuan Christian University sister university. So in these 4 years, so I visited second time. So this time I present my work. So my talk is a probing study in meson decay, basically recent LHC data. So my motivation so my motivation is direct search for new physics. In this case, especially the supersymmetry. So standard model explains successful CP violation of K and B methods. The standard model is the Kobayashi-Maskar model, in which is CK matrix is essential to predict the CP violations. So this is Wolfenstein parameterization of the CK matrix, and only one phase. In this case, is a phase is eta. So CK matrix is a unitary matrix. So we can write down the one of unitary relation here. So in this relation is expressed in the triangle in the complex plane. So B factory determines the unitary triangle on complex plane. So so the three angles were determined by the typical decay. So anyway, B factory determines the unitary triangle. So then the Kobayashi-Maskar won the Nobel Prize. However, there is still possibility to find new physics in the CP violation phenomena, especially in B surface system. So now is LHC era, so we can discuss the type scale physics. So we expect precise measurement of the CP violation in B surface meson. So we show the two unitary triangle. First one is B30 process. The three sides are the same order, but in BS case, the triangle is very different. BD case, two sides is the order one, but one side is a very small lambda scale. Lambda is 0.2. So very different triangle. So the CP violation is different in the BD case. And so now we parameterization of new physics. So at first, I add new physics. So we can express it in terms of the H and sigma Q, magnitude of the new physics, and normalize to standard model, and the new physics relative phase here. For Q is B, D, and CS. And in our analysis, we assume the absorbed part is just same as the standard model because we assume the supersymmetry, and then there's no effect on the tree-level decays. So this is the CKM at present stage. This is the unitary triangle here, and determines with the 20% level. This is the K-meson CP version epsilon, okay? And this is the mass difference of BD mesons, and so this is the beta here. In this result, there's no significant deviation in standard model, but there's a number of tensions, and there are many measurements can improve the load in the near future. Allowed region is much larger using only tree-level information. Tree-level information only gamma and VQ. Other information come from includes the loop effect. So at present, 20% new physics contribution to most loop processes is still possible. So for example, in BD, B-sub decays, the allowed region, new physics allowed region is here. Maximum is 0.5 HDR. This is the magnitude and this is the weight. This result is given CPM filters. So at first I briefly introduce the new data of CP variation. So as you know, the standard model like Higgs has already established, but there's no such evidence. But LHC is studying the B and D method of physics, and they found some CP variation, direct CP variation, and mixed and indirect CP variation. So anyway, so now we can discuss the indirect search for new physics. So there's some information of the CP variation in the LHCb. First one, the CP asymmetry is semi-elliptic decay, and this is a typical one, the non-elliptic decays, B surface to J psi phi and B S phi phi. We discussed these two processes. And there is direct CP variation. Today I did not discuss this direct CP variation. So I explained the CP variation in BS, the BS J psi phi. This is the CP conjugate state. So BS can indicate the final state J psi phi, but BS can also convert oscillation BS bar and then decay the final state, the same final state. Then this final state, CP variation of phi S divided by M and minus 2 phi D. This mixing with phi M, and this is the CP variation of S phi D. In the standard model, this phi S gives only one phase Einstein parameter eta. So result here, this is a standard model result. This is the phi S CP variation of phase. And this is a delta gamma mass decay with difference. So this is a standard prediction here, very small. At present, 1 sigma level, this circle 1 sigma. This is CP variation is given here. But now at present, it is difficult to test the CP variation in standard. And there is another CP variation, BS phi phi. BS phi phi indicates only loop effect, the penguin diagram. So this year, this CP variation reported this year. But this is first data rather than larger CP variation phase here. But this is the first data, so we should wait the improved data. I think it's this year. The data will be improved. So anyway, standard prediction is same order, the BS J psi phi. So because in the standard order, J psi phi, the phi phi decay is almost same order here, but very small, suppressed to the Chi-Wang scales. So now, can we find Suchi effect in decays? Is there evidence for new physics in B method? No. LHC and belt supersymmetry B are expected to observe the deviation of the standard model. However, at present, there are some tension between the K and B. So I explained the typical one. And this was pointed out by Brass a few years ago. This is the united triangle here. So pretty loop. This is epsilon K, the CP variation, K meson. And this magenta is delta M mass difference of the BD and BS equation. And this is beta is CP variation. So this allowed region is very small. So, in the standard model, the epsilon standard model given in terms of the Wolfenstein parameter, especially important is the CP biological phase eta. And mass difference of B meson is given here, Wolfenstein parameter here. And mixing triangle, one angle beta is this ratio. So it's a standard model. And the CP violation epsilon k is given in terms of the sine 2 betas. So now we plot. Important point. This is depend on the BK parameter. BK parameter is essential as a product. So this is the BK definition of the BK parameters, and then this is non-quantified physics. So the lattice calculation gives the result, the many results here, but recently the error bar is reduced. So most recent result of 0.73 plus 0.06. So using this BK parameter, we get this result, the epsilon k and sine 2 beta model. And so we put this data here. And predicted standard model, light green regions. And this is allowed region of the experiment, CP violation. And this red line is the epsilon parameter experiment, but divide the PK. So input is the mass difference of data. So allowed region is the small regions. So in the near future, if this result error bar is reduced, it is testable to the standard model. So this situation is modified by introduced by new physics. For example, in the Suji effect. So now we discuss the Suji contribution, but there is no evidence of the supersymmetry. But now mass band is increase and increase. So now we use this scenario, the split family. It's natural. Green mass is 1 TeV, and third family is also 1 TeV, but other is very, very heavy. So in our scenario, first and second family scope at the decoupled very heavy, and then contributes the green corpse bottom intact here. For example, the BS transition and right contribution, the BS bottom contribute. There is a left and right hand scopes, so there's two contribution B1 and B2. So we use the mass eigenbar B1 B2, and so this is a mixing matrix called bottom green mixing matrix here. So first and second family decoupled. The only B1 B2 contribute with parameter here, and this is the theta is left right mixing parameters here. So our scenario, large mixing left right hand bottoms, and this is our benchmark here, 1 TeV and another 1.1 TeV. And in that case, roughly we estimate mixing, but there is not definite. So we change the mixing 10 to 35 degrees. So in this case, bottom contribute on both delta B2 and delta B1 process. And in this case, green mass is fixed at 1.5 TeV. This is just low bounds of the present data. So, now we use the relevant constraint. For example, is mass difference epsilon k and the present CP violation here. And then we constrain the mixing parameter 2, 3, and 1, 3 element, and this is proportional to this product. And delta B equal 1 process here, BS gamma, for example, BS gamma, delta 2, 3. And especially, I use the constraint from the Coulomb EDM. Coulomb EDM given by in terms of the neutron electron dipole here. And this is constraint delta 2. So, and we use the relevant operator in the delta B effective theory. The effective theory means integrate out the heavy particle. So, for example, this decay mode is calculated using this local operator here. This part is also a question. In our calculation, we include the standard model Chrisitan coefficients and the musics scope interactions here. And we use the local operator. We use the relevant local operator. In our calculation, important is O1, O2, and O7 gamma, O8. So this is a contribution from the Grino as a Scope interaction here. This is a main dominant term here, and this comes from the left and right mixing here. So important point is the Coulomb EDM. So as you know, non-zero EDM of the neutron and the T vibrations. And the upper bound of the EDM constrains the Coulomb EDM of scope. Coulomb EDM means instead of gamma, campus gluons. So this was pointed out Hisano. And so this expression given here, using in terms of the mixing matrix element of the scope green equal induction here. So now this band given here, 2004 they obtained this band from neutron EDM. They used the acoustic sample and so on. Now the last year they improved the new data. 0.5 10 to 25 is there. And this is, we use this improved band here. So we show the numerical result. So using with the present band, we get the new physics contribution, the HQ and the sigma d, the phase, relative phase, and the magnitude here. So this is without EDM, without EDM constraints. So we get here. This is the PS and this is the B here. And if we put the Coulomb EDM, this band, Coulomb EDM constraint is very strong, especially for PS, B-surface. And so we expressed in terms of the mixing parameter delta 2,3 and delta 1,3 here. So we get delta 2,3 is 0.04 and delta 1,3 mixing 0.01. It's after present experiment. By using this mixing parameter, we calculate time dependent CPR symmetry. So at first, I explained the tension between CP variation K and the meson. So now we have another phase, new extra phase. So experiment observe the 2 beta, not the standard model. This is standard parameter of the CPM matrix. So we allow region given here. So it is allowed 0.90. And if so, in this case, it includes a new phase. So this converts inside the experimental allowed region here. So we skip. So we also predict the indirect shift variation in semi-electron decays here. So this is sub BD and sub BS. This is standard model prediction. This is our prediction, including a Suji effect. So this is it could be larger than for the BD decay, semi-electron decay. So it is testable in the future here. But present experimental burden given here. So now BS gamma constant not so strong because we show that this is a standard of prediction given here, but not so changed. So now important point, time dependent CPU asymmetry is here. So time dependent CPU asymmetry can be expressed in this expression. So now there are three experimental data. This is a tree level, this is a loop level, penguin diagram here. Then standard model, this CPU asymmetry is almost same with same within the few percent. So this case BD and BD Jefferson case and BD Psi case is given here. This is a tree level and the penguin one loop level, but this is almost same in the standard. But there may be deviation between standard prediction and expected result. So, but if we include the switch effect, different prediction. Because the final state parity is different here, plus and minus. So this it expects some difference here. So this is our predictions, our prediction here. So we use the heavy flavor average group data. PD, particle data group and the heavy flavor average group are somewhat different, especially here. But we use this data because they were not said. And due to the strong constraint of the epsilon parameter, the deviation is not so large. So the deviation is very small due to the Suji effect. But in case in the BS55 decay, only loop diagram, and BD KK decay here. So in this case, is could be large deviation. This red point is a standard model prediction, but it could be large or minus 0.2 and 0.2 here due to the Suji effect. And BD KK by also here. This is a standard point, but could be large. This is the upper bound of the experiment here. Now, this experiment data is very large. We should wait here. So, last. So, tension between epsilon k and sin 2 beta is solved by introducing the new physics, especially in this case, Suji. And then, this constraint, using this constraint, we predict the BS255 CP violation, time-dependent CP violation is around 0.2 positive to 0.2, which is much larger than standard prediction. So now, measurement of the BS55 data is only the 1.1 inverse of data 2011. So additional data now analyzing. So this year, we expect this year new improved data. So now LHC is still exciting and wait for the more precise data, the supercake will be very soon. Thank you.
Now, question. Okay, you mentioned this sin 2 beta extract from this golden model BPJ psi k and this B2E top K and 5KS. Almost equal in the standard model. I think this is, in general, this would be not the case because there was a pregnant pollution in this B2 eta 1K 0 and 5K short. This is, the population is much larger than that in a good mode between Jepside K. Even Jepside P2 Jepside K, they argue that there is some populations which you really couldn't compute. So I think the simple argument is that this sign to beta is checked from the three modes are equal. That is probably too simple. We couldn't expect that. In particular for B2 eta prime K, it is really difficult to compute these populations because eta prime is very strict. There is some global component. It is not so easy. Even for B2 Jepside K, we couldn't get such a conclusion due to this 3D diagram. There are three gluons emitted from this group, and so.
Sorry. Include some higher order Chrisitan, so of course it's some issue. Some not just seven, some different.
Your number is minus 0.2 to 0.2, right? But it's consistent with 0.
Yeah.
But why you said why you are saying the much larger is more prediction? Community.
Yes, at present, there is no strong evidence in deviation of standard model. By only we use experimental bound. So now it's still constant is the standard model. So result is equal to 0.
Okay.
Don't you have a tangent beta dependence in your study? Tangent beta dependence in your study?
Tangent beta is the ratio of the back excess bar. You mean?
Yes.
So in this case, we do not use the data of the tam beta because the tam beta dependence enters in the left hand, right hand mixing.
Right.
With tam beta.
But there is always favor conserving and the chirality free from the mu tangent beta term. And I think for the large tangent beta, this error is very large, so E2S gamma and D2D gamma will constrain very soon, I think.
So yes, we suppose mu tam beta is very large, but we not definitely is a constant tam beta.
Okay, that's thanks, Peter. Move to next talk by Dr. Chang. She's going